So let's take a look at the HVAC systems. You'll see that underneath ventilation there's two objects, HVAC template thermostat and HVAC template zone ideal loads air system. The thermostat is extremely simple. It's just three fields here. The name of the thermostat, the name of the schedule for heating, and the name of the schedule for cooling. So by now you know to go up to the schedule compact and you can find the schedules for heating and cooling. Here's the office schedule and residential schedules, and let's see if we can find the school schedules here. Notice that in the school schedules it has it's actually got a summer design day which you can ignore and a winter design day which you could ignore. There's also weekends and holidays and all other days. So all other days would include all the weekdays. So let's start here because this is where probably easiest to understand. The way this works for school is that from January 1st to June 30th, for all other days, meaning weekdays, from midnight until 6 a.m., the thermostat is set for 27 degrees. From 6 a.m. to 9 p.m., the thermostat is set for 24 degrees. And then from 9 p.m. to midnight, it's set back to 27. This is called a setback thermostat because during the daytime, it's set to a more comfortable setting, and at night, when fewer people are there, it's set to a less comfortable setting. Now, in fact, in Worcester Hall, we've got no cooling. And so one option would be to set this to get rid of this, but because of the system that we're using something called an ideal loads air system to handle all of the heating and cooling. And what this means is that, in fact, let me go back and show you what this means. The ideal loads air system here is this object, and there is, you can see here, no limit to the heating capacity and no limit to the cooling capacity. And what this means is that the system will provide as much heating or cooling as we need, no matter what happens, in order to achieve a certain temperature. And it will report what it used. Now and it's also a 100% efficient system, which is equivalent, say, to electric heating is 100% efficient. The exact amount of power that you put in is the amount of heating energy that you get out. Now, actually, 100% efficiency sounds like an efficient system, but it's really not, because if you look at electric systems like heat pumps, they can be 250 to 500% more efficient than the energy that you put in. So it's going to be important to take a look at that after we're done running the simulation in order to account for the actual heating, cooling system efficiency, because the simulation is going to assume it's 100% efficient. So there's really nothing for you to change in this ideal loads air system. I'd just like you to know that it's there, but all of these should stay as default entries or parameters. And really, the thermostat is the only thing that I'd like you to change if necessary. So going back to my school thermostat here, I was trying to make a point about the cooling system. In Worcester, there is no cooling system, and so what I would do practically is to jack this up to a very high number, like 40 degrees, and then I shouldn't get any cooling out of it, because it just means that if the indoor temperature is above 40 degrees, the cooling system will go on. Well, hopefully the indoor temperature never gets above 40 degrees, because that would be real hot. It is important to note that these temperatures are all in Celsius and they must stay in Celsius. So if you're more comfortable with Fahrenheit, then use a little conversion to figure out what temperature. By the same token, in the same way that we can adjust the cooling thermostat in order to eliminate cooling effectively, we can adjust the heating thermostat to eliminate heating by bringing these values way down. So say I had 10 degrees inside for heating, then I shouldn't get any heating. And in fact, let's just run this so you can see the results. So I'm going to save this as, I've been really bad about saving often, so please forgive me and don't do it like I do it. Do it better than I do it. Thermostat edits, I'll call this. And we'll run this. Well, these are old files I have open. Run this as a simulation and copy it into the dashboard so you can see what implications this has for energy use. So I'm going to open the table file and copy it to the dashboard under table. And I'm going to open the variables file and copy this to the dashboard under variables. And let's look at these in turn. I'm going to first look at the end use. So I'm going to copy this, Control C, to the InputOutput Summary, and I'm going to just put it here under people. I know it's the wrong category, but we'll be able to compare. And immediately you can see that by reducing the heating and cooling thermostats, I've dramatically reduced the heating, and it's actually hard to see what happened with the cooling, but let's look down here and you see that I've also reduced the cooling. The other numbers, the ventilation is different, and I can't remember if maybe I accidentally changed something. And the other numbers are all the same as they should be. And something to note as you do this, by the way, sometimes it's very difficult to see differences like that because I've got all these other numbers. So one thing I like to do is to copy this comparative use energy. So I'm going to press Control C, and then I'm going to paste this down here, Control V, and I'm going to erase everything except for the heating and cooling. And if I can't click on it like that, I go to Format, Category, Process, Delete, Format, Category, Hot Water, Delete. So now I've just got heating and cooling here to compare. It's still hard to see that the cooling is any different. It should be a slightly different number, 3.1, 3.5. Yeah, it's just not huge compared to the heating differences. You can see there versus there. But sometimes this is a little bit easier to see results for just heating and cooling as opposed to all of the different end uses. Okay, so that being said, let's look at a little bit more depth here. If we look at the annual use, you see that a lot of the heating went off in this area. We're still getting these little bits of cooling, and that is actually importantly during the part of the year that we haven't adjusted. Remember in that IDF file, let's go back to this, we adjusted for January 1st through June 30th, but we haven't adjusted after June 30th. And so you see that from January to June 30th, this has gone way down. Now it hasn't gone off completely, which is interesting. I wonder if we're getting some temperatures that are closer to 10 degrees inside, because it looks like it's going on when it's in the middle of the day. And we can look at that in another file. Let's look at this day, for instance, in the third week in February or so. Go to week, and let's go to February 18th. And you see here, if I zoom in, that the heating schedule is, so the gray is the cooling and heating. So you see the cooling is there, and the cooling is here and here, and the heating is here and here. And what's going on, it looks like, is that this is a weekend, and this is a week. These are the weekdays here. So remember, we just changed it for the weekdays, not for the weekends. So we are getting some energy use, and in fact, you can see this is the heating. So we're getting all of this heating energy, and then when the thermostat drops down, it drops way down. And it's very interesting to see that. So in spite of so we've got cold weather here, this black line, and then there's even some hours, you can see like right in the middle of the day here, where we are getting some heating in order to maintain that very low 10-degree set point. So you could set it for an even lower set point in order to completely turn the heating off, but know that it's real cold in there. I hope that is a good explanation. Please bring your questions with you to class. Now obviously there's a lot to talk about. So there's one thing we didn't touch on, where we started to talk about the fact that these systems are 100% efficient, the heating and cooling systems. Well, to account for that, I'd like you to account for them in this post-processing, in this Excel spreadsheet. So if we go to the Input-Output Summary, you can see at the very top here, I've got this note saying that system efficiency is a ratio of energy units delivered divided by energy used. See the HVAC tab of Model Inputs Calculator for approximate efficiency of your building systems, and then enter it here. So in the Model Inputs Calculator, if you go to HVAC, you'll see at the top here this table that lists each of your case studies and the heating, cooling, and hot water systems. And this is the best that I could estimate based on your documentation. Some of the documentation wasn't totally there. So there may be some, we may want to alter these as we learn more about the systems. Maybe you know more about the systems than I do, and then you can help, or I can help you to figure out what the correct COP should be. COP stands for coefficient of performance, and really what we're doing here is not just entering the coefficient of performance of the system itself, but also it's not the coefficient of performance of the machine itself, but of the total system, including the ducts and the pipes, the fans, the pumps, etc. So it is difficult to estimate, and I can help you with that. I've also got here down to the bottom a good rule of thumb estimator for different system types, different delivery types, and then some conversions between different faceplate markings. So we'll talk more about these towards the end of the semester, but this should be good enough to get you going. So for instance, if you are the Astana group, take these COPs, system efficiencies, 0.85, 3.5, and 0.94, and for and input them here, 0.85, 3.5, and 0.94, and this will, the heating and cooling in particular, will update throughout the spreadsheet. So I've used these in several places, most notably right here in your end use. What this is doing is taking the heating, the 100% efficient heating, and then dividing by 0.9 to give you how much energy you're actually consuming, and then the cooling, it's dividing by 3.5 to give you the amount of cooling that you're actually using. So as you can imagine, this is going to have a huge effect on your numbers. For hot water, notice that I don't have a system efficiency here, and that is because if we go to back to the Model Inputs Calculator, in domestic hot water, you will already have needed to account for that. So input your water heater efficiency here. What did I say for Astana? It was 0.94, so 94%, and that will change the total system efficiency here, which will then change your annual energy use there, which will in turn change your average power here, which is what you're actually inputting into Energy Plus. Okay, now that you have presumably a working model with all of the baseline conditions approximated, take a step back, congratulate yourselves, shake each other's hands, be happy, no severe errors, and I want you to then really begin the work, because one of the things about energy modeling in general is understanding the limits of how the model works. And this is really, it's a combination of a troubleshooting exercise and an intuition building exercise, so that you can understand better what are the push points of the model, where will it break, what are the problems with it, what are things that could be optimized. This is going to go a long way towards helping you understand what it is. And it's kind of like, think of it like playing with the model in order to understand it better. And the way that I've set up this, it's a particular methodology. And if you go to the Input-Output Summary, I've already explained this earlier in the tutorial, but I want to run you through it very quickly because I want you to see that it's really not that time consuming. It seems like a lot of inputs to go, through these, 14 different iterations. But in fact, you can do this quite rapidly. So I'm going to go back to the IDF editor. I'm going to not use my thermostat edits. I'm going to open my base file, which is here, Worcester 214. And I'm going to save this in a different folder. I'm going to make a new folder called Sensitivity Analysis. And just to make things really clear, and I'm going to call this 00 as the baseline. In fact, maybe just renaming this baseline.idf. And it's important to work from this as a base. So the first run that you're going to do here is called people. And what this is you want to eliminate people. Actually, I'm going to show you my example file here. What you want to do is take all the people out of your zone. If you've only got 1 or 2 people in your zone, then you might want to put people in your zone to see how the model will change. And so, as you know, the easy way to do this is to go to people, and instead of 25 people, I'm going to put in 1 person. If I put in 0 people, things might start to break. So I'm going to just put in 1 person to simulate what it's like with very few. So then I'm going to go to File, Save As, and I'm going to name this 01 people.idf. Done. Now, I'm going to close this and go back to the baseline because I want to then eliminate the next category, which is lights. So in the baseline, press Control L and go down to lights, and I'm going to change this to 1 watt per square meter. And now I'm going to save this as 02 lights.idf. And now I'm going to close this, and I'm going to open the next. I'm going to open the baseline again, and I'm going to change my next one, which is equipment. And you can go down the list. So 0 these out or make them very small. In this case, this really should say 1, 1, 1, like that. Now, for things like wall insulation, let's go back to this and save as, what number is this? 6. 06 wall insulation. Oops. Well, that's fine. And I'm going to go to my construction, and now I'm going to change the insulation. Now, in my base model, Worcester Hall has no insulation. So I've modeled it as 1 millimeter, very, very small. So in the sensitivity analysis, instead of making it very small, because it's already small, I'm going to make it very large. And I'm going to make this 1,000 millimeters. That's a ridiculously large number, but 1 meter thick of insulation will give me a sense of how important insulation is in the building. One note is, I think that if you go over something like 3,000 millimeters or 3 meters, the program probably will return a severe error. Actually, 1 meter might also be too big. We'll see in a second. So for the exterior wall, I'm gonna save this as 1 meter. If it does break, if you get a severe error, then just ramp it down a little bit. So instead of 1,000 millimeters, maybe it's 500 millimeters or something like that. So do that for the wall. Do it for the roof. I'm going to open the baseline again now. And for the windows, what I'd like you to do is change, there's 2 important components to windows. There's SHGC, or solar heat gain coefficient. That's how much solar radiation is admitted into the building through the glass. And there's U value, which is the insulative value of the glass. And so for SHGC, a higher number indicates more radiation. For U value, a higher number indicates more heat transfer. So I'm going to take my, I'm going to save my baseline as, sorry, what number is this? 08 SHGC. And I'm going to go to my simple glazing system, and I'm going to copy, this is my glazing system I've been using. I'm going to duplicate this, and I'm going to rename it to SHGC, just like that. I'm just going to change the beginning of it. And I'm going to change the solar heat gain coefficient from 0.66 to 0.1. I'm going to really change it dramatically. So now instead of letting in a good amount of heat, it's going to let in almost no heat. And we'll be able to see what things change. And I'm going to save that. Oh wait, before I save this, or it doesn't matter, I need to make sure that I've made this new material. I need to assign the new material as well. So here, under construction, make sure it's not just 3A. Actually, it just occurred to me it should have been set to 1A before. I'll change that later. But now I want to set it to SHGC, single clear aluminum. That's the one we just modeled. And for the shade, I want to do the same thing. I want to set this to be SHGC, single clear aluminum, like that. And now save this. And now close it, and now open the baseline. And I'm going to go back and save now a copy of 09 glass U value. And same type of procedure, we're going to go to the glazing systems, copy the one that we're using, or duplicate it, and then I'm going to rename this U value, oops, well, U value lim. These I had already made, so I'm going to delete these because they're a little confusing in this context. So I've got the U value one, and now I'm going to keep my solar heat gain coefficient where it was, but instead of this U factor of 7, I want to, that's a very high U factor, so I'm going to reduce this down to say 1. And that's going to give me a really good sense of what a much more insulative glass would do. And now I go to the construction, and here under glazing, I need to change this to the U value elim. I wrote elim because another word for this, another way of talking about this sensitivity analysis is an elimination parametric, because you're eliminating one value at a time, or in some cases you're increasing that value, you're isolating the value. So I'm going to save this glass U value. And now I think this gives you a good sense of how to go about this. I think the rest will be clear to you, the other parameters of how to change them. But now that we've got all this, you can go to that folder with the sensitivity analysis and click each one, make sure your weather file is set to the correct weather file, press simulate, and then while it's in progress, you can actually go to the next one, browse, and click on people, simulate, and let it do its thing, and then click on the next one, lights, and simulate, and I forget where we are here. Anyway, you can simulate all of these simultaneously just by clicking through, and this is a much faster way of running them all. And then make sure, however, when it gives you the dialog box, that you're checking the warnings for all of them, making sure that it's the same warnings and you understand them. There's no severe errors. In this case, there is. And now you'll notice that if you go to your sensitivity analysis folder, there's a lot of files in here. For every IDF file, it actually makes all of these files. So there's the IDF file, and makes all of these files associated with it. Remember when you clicked on that error message before, there's that 00 baseline.error. If I double click on this, then the error dialog box comes up. So what that EP launch is doing, it is referencing these files here. The ones that we're concerned about, tables, variables, and errors, are errors, and then the tables and variables are the two CSV files. So here's the table file, .csv, and here's the variables file. And another way of doing it, so you can see there's both CSV files. So if we change these to organize by type, and then go to the CSV files, you can find all of the CSV files for all of the runs. And in fact, for the elimination parametrics or the sensitivity analysis, we're really just concerned with the table files. So we can click on those, and then I'm going to hit enter, and it'll open all three in Excel. And it's possible, I'm waiting for my computer to open them now, to do this kind of rapid fire where we've got the baseline file. I'm going to copy this into my dashboard under table, go to end use, copy this to your input-output summary, your graph, then go back to table, go to the next table, 01 people table, copy these, go back to the dashboard, copy, go to end use, copy these guys over to people. Then go to lights table, .csv, copy those, and in your dashboard go to back to table, paste, end use, copy, summary, paste. And hopefully what you'll see, which is good, we're actually seeing some differences here. When we eliminate the people, you notice that the heating went way down. And then when we take out the lights, or most of the lights, the lighting goes way down, but the heating goes up. So I'll leave you to reach your own conclusions about why. But what's important is when you output these files, I want you to output them to PDF and then save them in an InDesign document, and then write annotations for why these differences occur. I'll give you a hint. In this one, the heating is going way down because, remember, the ventilation was tied to the occupancy patterns. So as you have more ventilation, you introduce more cold air, which then requires more heating. And so as we reduce the number of people, we reduce the amount of ventilation, we're also reducing the heating. And so it's not important really that you're making these larger, it's not important that you're reducing the energy use in all these. What's important is the difference from the baseline. So you can see in this that the model is very sensitive to ventilation because of the people, occupancy patterns. And if we can control ventilation, then we can have a better shot at reducing the energy in the long run. You can also see the model is relatively sensitive to lighting energy, which also gives a hint that heating is really important, because right now we're using the lights to heat the building. So if we could have a more efficient heating system, we could, and maybe more efficient lighting system, we could dramatically impact the overall energy use. All right, so that's the end of this series of tutorials. I hope this helps. Please write down lots and lots of questions for me, and on Thursday, bring them in. We can discuss them. Good luck. Have fun.